Welcome to this session. In this session, we discuss the solution to the card that we've done on 16th. So the first question was, let U be the universal set, and let A and B and C be any three arbitrary sets or subsets in U. Use a Venn diagram to represent the following sets. Now, one of the key things that this question was testing on is whether you know how to interpret problems. Because they have already specified that it's a universal set U, then when you're representing the sets given in Roman 1 and Roman 2, you must clearly show the universal set U. So if you don't show the universal set U, then you don't score on this problem. So we'll draw this rectangle to represent the universal set. So this is the first Roman, A complement intersect B union C. So let this be the circle that represents set A. Let this circle represent set B, and let this circle represent set C. So to define the third region, let's start by understanding what you mean by B union C. So B union C means all those elements within the C circle and B circle. So they may be purely in B or both B and C. So if I name this 1, 2, 3, 4, 5, 6, 7, then the region that defines B union C is 2, 3, 6, 5, 4, and 7. A complement means what is outside A. So what is outside circle A is region. So remember we have said that B union C is the region 2 plus 3 plus 5 plus 6 plus 4 and then plus 7. And then A complement means what is outside A. Now what is outside A is this region 2, this region 3, region 6, region 7, and region 8. So the intersection means common point between A complement and B union C. So what is common between these numbers? We have 3, we have 6, we have 7. So we shared region 3, region 6, and then region 7. So those are the common points to these two sets, A complement and B union C. So this 3, 6, 7. So the shaded region defines the area or define the set A complement union intersect B union C. So this is how we present that set. If you draw this, assuming you draw this as set A, and then this as set B, and then this as set C, and you shade if you do this, this will be wrong because you have not shown the universal set, yet the universal set was specified in the problem. So this will not be accepted because there is no universal set specified here. And then Roman 2, A intersect B intersect C, you must show the universal set because the question specifies that all the three sets A, B, and C are within the universal set U. So you must show the universal set. If the question didn't specify the existence of universal set, it was just now to show the region, then you are allowed to use either case. But once the universal set is specified in the problem, you must show it. So let this be set A. Set B. This to be set C. So A intersect B intersect C means the region which is common to A, B, and C. And is this part. This is the part where A, B, and C share. So that is the solution to that part. Part B in the cut, we had proof the following. Trigonometric identities. This was part B of question 1. So the first trigonometric identity was tan of A plus B is given by tan A plus tan B over 1 minus tan of A, tan of B. And Roman 2 was to show that 1 plus sine of 2A is equals to sine of A plus cosine of A squared. Now, to prove the first trigonometric identity, you remember that. So proof tan of any angle theta is the same as sine of the angle divided by cosine of the same angle. So when you let theta to be A plus B, then it means tan A plus B will be the same as tan sine of A plus B divided by cosine of A plus B. And by definition, sine of A plus B is sine A cos B plus cos A sine B over the cosine of A plus B is cosine of A cosine of B minus sine of A and then sine of B. So which means that tan of A plus B is the same as sine A cosine of B plus cosine of A sine of B, cosine of A, cosine of B minus sine of A times sine of B. Now what we do to this expression, we multiply it by 1. We multiply it by 1, but this one we write it in a special way that will help us to do the simplification. So I'll multiply the numerator by 1. So I'm saying 1 over cosine of A times cosine of B. And I also multiply the denominator by 1 over cosine of A, cosine of B. You see, this is the same thing as saying I'm multiplying this expression by 1 over cosine of A, cosine of B, over 1 over cosine of A, cosine of B. You see, this is just the same as 1. And when you multiply 1 by an expression, you don't change the value of the expression, but we are writing it in a special way that will help us to do the simplification. So this means that tan of A plus B is the same as, so this 1 over cos A cos B multiplies every term. So we have sine A cos B divided by cos A cos B plus cos A sine B divided by cos A cos B over cos A cos B divided by cos A cos B minus sine A sine B divided by cos A cos B. There's no miracle performed. If you simplify this expression, you go back to what we had, sine A cos B plus cos A sine B over cos A cos B minus sine A sine B. But by this computation, we see that this part now will give us 1. And this one cancels out. This and this cancels out. So that we have tan of A plus B is equals to, here we have sine A over cos A plus sine B over cos B. This part is 1 minus, this can be written as sine of A over cos of A times sine of B over cos of B. And we have said that tan theta by definition is sine of theta over cosine of theta. So then this implies tan of A plus B is, here will be now tan of A plus, this defines tan of B over 1 minus, this defines tan of A, this defines tan of B. And that is what we were to prove. Part B, we are to show that 1 plus sine of 2A is equals to sine of A plus cosine of A squared. So this is how we prove trigonometric identities. You can either play with one side or manipulate one side and see that the solution you have is same as what you have on the opposite side, or you can manipulate the two sides differently, but see that the simplification converges to the same answer when you do for both cases. So in this case, left-hand side, we have 1 plus sine of 2A. But you see 2A is just the same as A plus A. So this is the same as 1 plus sine of A plus A, which is the same as 1 plus sine A cos A plus cos A sine A. We know that sine of A plus B is the same as sine of A cos of B plus sine of A cos of A, then sine of B. So when you let A to be B, that's why I have this. And you see this will be the same as 1 plus, this will be two of them, 2 sine of A cos of A. Now, right-hand side is given as cosine of A, sine of A, plus cosine of A squared. Now, this is the same as sine of A plus cosine of A multiplied by itself. This is the definition of a square. So we'll have sine squared A plus sine A cos A. Cos times sine is sine of A cos of A. Cos times cos is cos squared A. But you can rearrange this one as sine squared A plus cos squared A. These are two of them, 2 sine A cosine of A. But we know that sine of theta, sine squared of theta plus cos squared of theta is 1. So this part is just the same as 1 plus 2 sine of A cos of A. So this is what we have on the right-hand side. But you see, the answer we have found, the simplification on the left-hand side agrees with what we have as simplification on the right-hand side. So you conclude, since left-hand side equals to 1 plus 2 sine A cosine of A, which is the same as right-hand side, then the identity holds. So that's how we prove that. Next session, we'll give the solution to the next problem. Thank you.